Thank you, Will.
And
Thank you,
we
everybody.
are recording. Okay, good.
And I think I met some of you, some not. As Will said, maybe we're gonna meet at some Cal Poly course. If not, we're gonna meet somewhere around airport or airplanes, because that's what I like to do. If you have a camera, put your camera on so I don't speak just your computer. And Will just got me on the hook last week to talk about something. He didn't specify what. He just said, go talk about something. And what I decided to bring to you is exactly what we, not exactly, but I'm going to use the same presentation that we use on the Society of Experimental Test Pilots about a month ago, I believe. Yeah, exactly a month ago. So I did a presentation with Jim Payne, and we talk about testing Nixus. So what is good here is I'm gonna just talk about what we did over the summer. Ideally, I would like to have you guys there with me and Jim flying Nixus, but of course, COVID and class, you guys were not able to go. So hopefully next year we're gonna be able to do this again. But it was a really nice time. Actually, I can open this. Let me take a look so we can get real numbers here. But we did since, let me see here, since May of 2020. So that was I don't know how to say that in English, flight number 20. So we flew 24 times during the summer. And at this time, we had a total time on the airplane of 47 hours. And we end up the summer with 195 hours, so 150 hours during the summer. Of course, this is due to Jim Payne. Every flight that Jim flies is 7 hours minimum. Never goes for less than 7 hours. In the middle of those flights, we did a lot of testing. Some tests for the very specific parts of the airplane, but some tests just operational tests, just go fly, and having Jim trying high performance flights just to see how the airplane behaves. And it was actually pretty successful. We did, so first day that I got there was actually the last flight that I did with Morgan. The first day, Jim just got a wave, and it was about 1,000K flight, a very fast one. Then the next day he did 1,000K, not a triangle, but a normal 1,000K. Then we did a 1,000K triangle, and we end up a little bit short, had to land in Reno Stad Airport. That was actually very funny for me because, I was always involved with race planes, and a big dream of my path was to take an airplane to Reno. So it was the first airplane, my first airplane that I took to Reno, not a race one, but a glider. And then a few days later, he did the 1,000K triangle, which allows you to do 3 US records. Then a few days later, the big wave flight it was actually 2,400K, but we lost avionics at the end of the flight, and we had to throw one leg on the trash because of the 5 turning points. That flight gave us 750 out and return record. And all those records are US records for the multi-seat open class. And then later he did another 1,000K triangle, and the very big one last time was 750K triangle. So a lot of big flights. But we tried to do that with as much engineer we could use. So that's what I want to show a little bit today. If you guys have any questions, just open your microphone and ask whatever you want. Let's do this more like a conversation than a lecture. I'm gonna jump this because we just explained the project, and I think everybody, if you don't know the details, we can talk about the details later. Let's concentrate on the testing. Okay. Let me go here. Before we talk about testing, I think it's interesting to talk a little bit about the fly-by-wire so you can understand what are my data acquisition capabilities. And this shows a little bit of how the fly-by-wire works. And what's important here is that I have 3 computers running parallel all the time. They are actually physically inside this box that goes under the rear seat on the right side. And everything that's going on those computers, I can save. So I have all the information that goes to the fly-by-wire and comes back from the fly-by-wire. All the sensors that I use on the fly-by-wire goes on those computers. I have that information. So this is one of the big sources of data that I have on the airplane. This data is being recorded at about, I would say something between 10 and 20 hertz. It's asynchronous, so it can vary a little bit. But let's say I have data here at least at 10 hertz, which is pretty good for the dynamics that we are looking for on a glider. You can imagine a 7-hour, or 8-hour, 10-hour flight. The amount of data that this generates is huge. So go back and dig into the data. It sometimes represents a big challenge for us. On top of that, we have another system that I don't show here. And actually, I don't show here either. But we have 2 battery monitors. So you can see the system had 2 batteries. And I have 2 battery monitors on top of those batteries that I can measure the current and the temperature of the batteries and what is the voltage. So therefore, I have power and power consumption. And so that information also go to another data logger. And that data logger, I add a few more sensors that I don't use on the fly-by-wire. So that those 2 data acquisition systems are kind of particular of Nixus. So it's systems that I develop. So I have completely freedom to do whatever I want on them. And then the third source of information can be the LX. That normally records an IGC file. Normally, I don't use the IGC for a lot of stuff because the sample rate is not very high. But sometimes it's useful. For instance, sometimes I lost data on this guy. I actually lost data for a very stupid reason. There is a SD card. The SD card has a file that sets the bound rate for the data logger, and I just saved the wrong file, you know. And when I lost that data, having the IGC file, it's very, very useful to try to reconstruct something that I don't have that. So I have one flight that I had to do that was very, very useful. So and here you can see a typical testing day. Actually, this was still in SLO, but I was preparing to go fly. And extra stuff that goes on the second data logger that I mentioned is like, for instance, a load cell on the stick. You can see here this red knob. It's a secondary stick that has a load cell that I can measure aileron and elevator forces. So all this goes on the second box. So that information does not go on the fly-by-wire system, but instead go on this data acquisition box that I have there. Okay, so yeah, for those who never saw this, let me just change this. Let me open the PDF file actually, because then I can, not the PDF, the PowerPoint file. Yeah, for those that never saw the the wing breaking. For you that never heard about this, so I built this wing and we test the wing, and unfortunately I broke the wing, so I had a design mistake. So just showing this, and this is when I came back to Cal Poly, and we rebuilt the wing. Okay, so now let's talk about the flight. So just a recap, Nixus flew first time in March 2019. Then on the tow plane, Jim Payne on the glider. A lot of Akafliegers on the ground. And we came back to Kessel, I believe, 2 or 3 more times. One time I remember we give up on a flight because we are not sure about the aileron control system, so I improved it. Then we have a landing gear failure in Kessel. That was about April, I believe, or maybe May of that year. And that was the last time that we flew in Kessel. After that, we moved to Minden, where we finished phase 1. And what is important to mention here is all those flights, which we can see on my flight log here, that was from March 2019 to July 2019, or June 2019, we had a very, very limited maximum speed. So 80 knots was the limit. And basically what we are trying to do is to achieve confidence on the fly-by-wire testing.
Hey, Paulo, I have a question.
Go ahead.
Where did you come up with the 80 knots number?
It's based on my VN diagram, and was a huge margin in relation to my VNE that based on my flutter analysis, computational analysis, I was comfortable with. So of course, we on those flights, we never went straight to 80 knots, but that was like a hard limit for Jim. And he approached that 80 knots cautiously. But at this phase, there is no testing to check if 80 knots will work or not. The check was, if you want to fly close to 80 knots, go do that high and be ready to get out.
Cool, thank you.
So after this, just to give you an idea of how the flight test works, then Jim did 2 more flights in Minden, which one of those flights was kind of a long, let's see, probably this one, a 5-hour flight, where he kind of stretched a little bit, not in terms of speed, but in terms of distance and getting comfortable to get out of the safe cone around the airport. And so this was an important flight for us to build confidence on the fly-by-wire, measured power consumption, and that type of thing. And then Morgan started to fly in August, end of August, the start of September. And then we had a series of 5 flights with Sergio, the owner of the project. At this point, we kind of stopped. That is September 2019, and we only start to fly again in January 2020. So during this time, I did a lot of small improvements on the glider. And when we came back to flight, the first thing that we did was to do a CG test that I will talk about it, and the beginning of the flutter test, okay? And I will talk a little bit, what is this flutter test? But this just to give you an idea that it's almost 9 months making 14 flights, which seems very small number of flights, but you trust me, it's a lot of work and a lot of small details here and there that I had to fix or adjust or improve to make the glider ready to go to actually test and perform. Oh, and one of those tests, Zach was there with us, was the ground vibration test that happened in October, and beginning of November at 88. So this test, what happens is, the idea is, for those who don't know, we have a structural model that we build for this glider. And the structural model is able to determine what is the natural frequencies of the structure. So if you put the structure to vibrate, what is the frequency that the structure vibrates? The same structural model that we have for the structural analysis in this natural frequency is the one that we use for flutter. And what flutter is, basically what the model does is to calculate the new frequencies, natural frequencies, but not for a free vibration, but instead for a forced vibration. And where the forces come from? The forces come from aerodynamics. And of course, it's really hard to measure if that model is correct or not. So what we do is a building block approach, okay? So the first step to make sure your model is correct is to do a frequency test on the ground, free vibration, no force, and check if your model correlates to that. And this is exactly what we're doing here. We put a bunch of accelerometers on the glider, 148 accelerometers. And the glider is hanging on the air. It's kind of hard to, I don't know if you can see, there is this crane here, the yellow crane, and the glider is hanging on bungees. So it's flexible to vibrate. And then we shake the glider. There's shakers, electromagnetic shakers, and you shake the whole thing, you measure the vibration. And then you compare that vibration with your model. And you compare two things, the frequency and the displacement. And if your frequencies and displacements match the model, it means your model is good. If not, it means you need to do adjustments on the model. The way that we do adjustments, there are techniques to do this automatically. I don't know how to use the techniques. Mine is try and error, you know, just spend a weekend in front of the computer trying different things. But basically, I change the mass distribution and the stiffness. So where I see the frequency is kind of high, I either add mass or I reduce stiffness. And it's kind of an easy process because if you weight all the parts, you know the mass. And so you can do the adjustment of mass really easy. And then if it's not matching, you just do the adjustment of stiffness. And first time that you do is kind of hard. After the first time, it's almost intuitive and it goes really fast. And actually Nix's model was really good. I have only 2 or 3 modes that were more than 5% off in terms of frequency. So it was really easy to adjust that. And what you see on the left side is a comparison for one of the modes. In this case, mode number 5 for me on the GVT, which is probably the second bending of the wing. So you see this image here is the GVT results measured with those accelerometers. And on this side is my computer model, okay? As you can see, it's really, really similar to this. On the GVT, we also did a test comparing the system with the fly-by-wire on and the fly-by-wire off, because the way that the fly-by-wire works, let me see if I have a picture of that here, is the flap deflection is based on lift coefficient. And to calculate lift coefficient, I need to measure the acceleration of the airplane. So when my airplane is vibrating here on the bungees, the acceleration is changing. If the acceleration is changing, it means the flaps are moving. So if the flaps are moving, my response, my frequency response will be different. And we measure that, and you see a small difference in some nodes, but in general, it's not big. So this is not really significant for us. The amplitude difference is not very important. Frequency difference are the one that are very, very important for me. Okay, so we did this in November, and then we went to fly again. And when I told you that on those slides here, we're doing flutter tests, the goal for this is now to measure the vibration in flight. Okay, so let me jump to this chart here. Actually, let me do this more. Let's open MATLAB and do real life stuff here. So I will show you what is the result of a flutter analysis, okay? And then I will explain how I measure that in flight. So if I go here to my ship mixes, okay, this is the typical result that I get out of a flutter analysis. It looks like crazy stuff, huh? Look at this chart. Can you read something on this? Nuts, I know. So what is the idea? It's actually very, very simple. After you understand what it is, it's super simple. So this chart first, okay? This is frequency on the vertical axis and true airspeed on the horizontal axis. So if this goes all the way to 0, the frequency that you see here is the natural frequency of your structure. As you start to increase the speed and the air start to produce some force on the structure, those frequencies start to change, okay? And you can see really clear that there is a frequency here that kind of drop a lot until it hits another one, and then they kind of diverge. This is where flutter probably is. What happens here is, imagine that your wing can flex like this and can twist like this. If those two movements, flexion or bending and torsion, are happening in different frequencies, there is a very low probability that when your wing is going up, it's also pitching up. Because if it does this and pitch up at the same time, the load is increasing as the wing pitches up and wants to bending up, wants to bend up the wing even more. And this is what flutter is the self-excitation of your structure. So if your bending frequency is different from your torsion frequency, the probability that this coupling will happen is very small. But when they become equal, then they're gonna diverge. And this is what happens. This torsional frequency starts to reduce, and at a certain point, it couples with a bending frequency, and that diverges, okay? That's a very, very simple explanation of what flutter is. And so what this allows me to do is to go back on this second chart, which is damping with speed. This chart starts at 0, so it's important to look at where is the 0. And normally all the damping of your structure is negative, means the structure is losing energy. When those two frequencies couple, then you're gonna see some of those modes diverging in damping. And what means now is the damping is positive. What positive damping means is not damping, it's the opposite of damping, okay? So what a flutter test is, I have two options for my flutter test. I can either keep measuring the frequencies of my structure while the structure is flying and see if the variation of the frequencies that I see in real life are equal to the variations of frequency that I see on my flutter test, my flutter analysis. Or I can measure damping of certain modes, and based on the damping measurement, I can try to extrapolate, or based on a sequence of damping measurements, I can try to extrapolate where the damping will cross the 0 line. So I see my damping coming down, 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 until the point that will cross, or thinking about this direction, my damping going negative, 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 coming up, up, up. When you cross 0, that will not be my flutter, okay? Measuring damping, it's more difficult than measuring frequency, okay? And it's all about how much noise you have in the signal and how you dealing with the transformation between the time domain to the frequency domain. So I must confess, I'm still learning how to do that. I tried to do damping, I could not. It's very, very interesting. A few days ago, I was contacted by a person, and I knew that person had published an article about Flutter. And my contact with this person was completely out of the blue, not related with Nexus at all. So I went to this meeting with this person, and on the meeting, he told me, oh, I did publish an article about Flutter. And I thought, oh, by the way, I need some explanation how you did this. And the guy told me how to do it. So now, next time that we're going to test, I'm going to try that. But what I'm doing right now is just looking for the frequency. So
Now,
how I did that, go ahead.
is that measured data you were plotting there, or is that data
No.
from FEA?
This is FEA. This is
Okay.
all data from the FEA, okay? So now, how am I going to do this measuring? So Nexus had a very challenging configuration that is very small wing, very little access panels inside the wing, and very long. So if I want to do a data acquisition on the wing, it will be really hard to run cables on the wing. So I try many times. I went to Scaled Composites and I asked help there. And those guys were very helpful, but complicated to get access to their system because they're busy with other projects. And I said, you know what? I better solve my problem by myself. Otherwise, I will never solve this. So what I did is I built this little device that goes inside this 3D printed pod that I can just glue to the wing with tape, just attach it to the wing with tape. And what this device is very simple Arduino reading 2 accelerometers, and I put one accelerometer on the leading edge, one accelerometer on the trailing edge, and I collect the data really fast, about 250 hertz, and I bought a little radio. That's the beauty to be in the United States, you just go on Amazon and you buy those stuff, and it comes to your house. Try to do that in Brazil. It takes like 5 months, and it's 78% of texts. So I just bought that thing. It's a little radio to send the data to the cockpit. And on the cockpit, we have this little screen that I can either log the data or do the FFT, which is a transformation between the time domain to the frequency domain, and see where are those frequencies or where the wing is vibrating, okay? And it ended up being a very neat system, and I'm really happy with the results right now. And this allows me to do this. So now it's a comparison between the chart that I just showed you, of course, cropped, so it's a small range. And those are the frequencies that I'm measuring, okay? Because I only have 2 accelerometers here now in comparison with the 148 that I had on the GVT, I can't measure all the modes. There are some modes that I need more accelerometers to measure.
Hey, Paulo,
Yeah.
does each curve represent a mode?
Yes, each curve is a mode.
Okay, thanks.
Yeah. But we can see some of the frequencies. And the most important one, I can see this one. And I can see it's coming down. You can, based on the data that we have right now, I see it's coming down a little bit faster than the phi model. So you see the difference. So here they're kind of on the same spot, and then they kind of coming down faster. So I predict that maybe will not be my Flutter prediction would not be exactly the one, but I still have a lot of margin on this, okay? So the next steps on this, so this allowed us to open the envelope up to 140 knots, 130 knots, come on, 130 knots. We did collect data up to 136 knots, okay? but we're okay, we're clear to go 130 knots, indicated airspeed up to 21,000 feet, okay? I want to get at least 45 knots more on top of that. So it's still a lot of work to do, but it looks very, very promising. And what is the work to do? The work to do is to make sure this data is correct. So we need to repeat those points and make sure we get exactly the same. Probably improve the system to do the damping measurement now, and then do more points at higher speeds. Okay, so this was a big part of the project during the summer. Put this to work. When we first did this, it did not work in Paso. Morgan did one flight with Jim, and I think the whole thing was just not working at all. Then I managed to make it work. And as we collect data, I'm learning a lot of stuff, and I'm learning how to actually process the data. And so I'm pretty confident that we will get good results and allow us to go faster in the future. Okay. And also it's important to mention all those points that you see here is not one flight. It's a sequence of flights. So we collect data here, and everything was good. Then we collect data here, everything is good. Then we collect data. So it's progressive getting there. Okay. Any questions about this?
I have
I have a question.
Oh, go ahead.
Can
Go
you
ahead.
explain why some of the modes don't change frequency with airspeed and some of them do? Are some of those like fuselage bending modes and some are wing?
Most of the modes that I'm showing here, or all the modes that I'm showing in this particular graphic, are wing modes. And some of the modes, like most of the bending modes, they have a very small variation with speed. The torsion modes are the ones that are very change a lot with speed. That's the best explanation that I can give to you.
Okay.
It's not always like that. That's just particularly of this wing. But in general, bending moment does not change much.
Thanks.
Or bending mode, sorry. You have another question, Will?
So how exactly were these excited? Was it using
Oh, that's an excellent question. So we actually did two types. So the very first time that we went there was just a stick wrap. So you just put on the speed and tap the stick and let it go. But then it's always the question, are you exciting the wing like the wing should be exciting or not? So then I start to build eccentric mass. So it's pretty much just, I don't think I have a picture here, but it's an eccentric mass, and I put that on a step motor, and the same device that does the data acquisition system is start the step motor. The step motor just starts to increase the speed, like a cell phone vibracall type of thing. But the mass that I have is very small because it needs to fit on one of the inspection panels that I have. So it's really small. And at high frequencies, you know, the force is proportional to omega square, the rotation speed square, centrifugal force. So at high speeds, that mass had enough force to vibrate the wing. But at low speeds, it did not. So what I did is I changed the fly-by-wire code for one servo, and on the button that Jim had to trigger this data acquisition system, I duplicate the button, and that button also communicates now with the fly-by-wire system. So when you press the button, the flap number 5 starts to do this, and it shakes the wing. And of course, the servo cannot excite the wing at very high frequency because the servo is not fast enough. So we had both systems assembled at the same time, and they kind of, you know, excite the wing together when we're doing that.
Okay, and one more. Go ahead.
I just, out of curiosity, since you're fraternizing with Jim Payne, Morgan Centercock's capability to excite the wing of Perlan, you couldn't do that with a Nixus because out on the tip, you didn't have access to it really. I mean, Morgan embedded his in the wing, but I wonder, he did quite a bit of ingenuity to get that flutter tester on the Perlan. I just wondered if it was applicable for you.
So my first approach was to call Morgan and ask him his system. So that was the first thing that I tried, and it was too big to fit inside Nix's wing. And then Morgan also needs to have the batteries inside to power his system. And I could not, no, what it was to do, no, he needs to run wires. So he needs to have a wire data collection system. So I could not run more wires inside the wing, not because they don't fit, just because the wing's closed. It's hard to run the wires inside. And that's what drove me to build the wireless system, is to allow, to prevent you have to run wires inside the wing.
Was there any worry with the wireless system that the mass out on the wing might change the vibrational modes?
Well, the wing weighs 300 kilograms. That system weighs about 10 grams. So changes, yeah, it changes, but not significantly. Yeah. So here's the typical excitation result. So this is time domain. So it's seconds. And you can see where the flyby wires start to excite the wing, and then the mass comes up, and then they shut off. And I use the data after the shut off to generate the frequency domain result that gives me the response of the wing. And this is the force, excitation force produced by the mass, and the excitation force produced by the flyby wire, and how they kind of combine and give me enough level of force to excite the wing. So everything about 5 pounds I can measure. Okay,
Paulo,
so go ahead.
One of the tests we did back in January was a level deceleration test.
Yeah.
What were you looking for with that test?
Okay, let's talk about that one. So we're doing the performance analysis of the glider, okay? So what is the idea? Let me go back here and show that. So I hope you guys can see this plot. The lines are kind of a little bit thick. But what is the level deceleration? The level deceleration is, this first chart is time with altitude. Okay, so glider took off, tow, climb, switch on the engine, climb a little bit more, go really high, 10,000 feet, and then start to do some testing here. At some point, you see it dives like crazy and fly level. Okay, why he's diving like crazy? He's diving like crazy. If you look at the second chart, time with airspeed, he's going to the maximum speed, 140 knots, 130 knots. So he's now at very high speed, and now he's trying to fly as level as possible. So we built a little display that has a flight director, and it tells him where he needs to put the nose to fly straight. So now he's flying straight, and his potential energy is constant or very close to constant. Agree? But his kinetic energy is reducing. What is the only thing on a glider that makes kinetic energy reduce? Drag. If we didn't have drag, you're going to keep your kinetic energy forever if you don't climb. So if the atmosphere is completely calm, and I can measure how fast he's decelerating, I can calculate what is the drag. And actually, I'm going to go a little bit on the math of this because it's actually very, very simple. So the total energy of a glider is potential energy, which is mass times gravity times weight, height, plus kinetic energy, that is half of mass times velocity square. Okay? Divide energy by weight. Then you have this, I call ES, specific energy. Is potential energy divided by weight, kinetic energy divided by weight. So agree that energy is force times distance. If I divide energy by weight, I'm getting force times distance divided by force. Weight is a force. So specific energy has units of distance. And we actually use this as a height measurement. Okay? So if I do a derivation of this over time, I now have variation of distance by variation of time, which is a velocity. What is this velocity variation now, or velocity number now? Is the variation of your height, which you can prove that is exactly your sink rate. So that's the level, that's a technique that we are trying to use to measure drag polar of a glider. Okay, so we have a way on a glider to measure height and true airspeed very precisely. Okay, the height we measure with a high performance GPS. We could use pressure to measure height if we know the pressure variation on the atmosphere. For now, we're using GPS. The true airspeed, I use two techniques. I either use a high precision GPS, and then I correct with wind speed that LX is calculating, or I simply get the airspeed indicator of the LX and I calculate true airspeed. Those are the only two things I need to measure. And then I need to do the numerical derivation of this energy in relation to time, which is kind of a little bit tricky because every time that you do a derivation in numerical data, you get a lot of noise, okay? But we did some, and I'm not going on the details of this right now, but we did some math to fit some polynomials that we know that we expect a drag polar with a parabolic shape. So if the drag polar is with a parabolic shape, what is the shape of the speed polar? So we use that and we can do the derivation on a polynomial, which is smooth and has no noise. And then what we get out of that is results like this, okay?
Hey, Paulo,
Yeah.
do you have any comparison of sawtooth descents with the level decels?
No, I don't have. The sawtooth descents, the problem is you're going through the atmosphere. So the atmosphere might be changing as you come down, especially close to the ground. The advantage that we see on the level decels is the atmosphere that you're flying is pretty much the same all the time. So you don't need to worry about that. Make sense?
Yeah, that makes sense. Thanks.
So what you see here is the speed polar for Nixus. Okay, so that's the first time that I published those numbers. Black line is my prediction with a perfect glider, no cracks, no gaps, nothing, no tape. So if we can get there, I'm really, really happy. The blue, the yellow, and the orange line are measurements that we did with this system. And the dashed line is the average of the measurements, okay? So I was expecting 70 to 1, and I'm getting 67 to 1. It's kind of okay for something that a professor built. Good enough.
All right.
What is really interesting is the high speed performance, which this glider should not have a very hard kink here that normally the other gliders have. Nixus seems that it doesn't have, so it performs really well at high speed, which is what we're looking for. Can I still improve this? Yeah, sure, I can still improve. There is some questions about if I should get more flap deflection to get at lower speeds here. There are some questions about miler that we're trying to investigate if the milers stay attached or not. There's some finishing work. But just to give you some perspective, we're talking about measuring here. So at high speeds, we're talking about 0.5 knots of vertical speed. So try to measure the drag force to accomplish this. I'm talking about less than a pound of drag force that I need to take out of the glider. And that's where it becomes really challenging. It's so sensitive to everything, including atmosphere, that it's kind of hard to be consistent on that.
Paulo, have you guys planned any sunrise or sunset flights to take out the atmospheric noise?
This flight was 10 minutes after the sun rise. So if you look the takeoff time here on my flight log, 6:46.
Yeah, you can't do much better than that.
No, unless we go illegal. Yeah. And did you see the altitude that we did the flight? So he towed up to 9,000, and then he switched on the engine and went up back to 10,000. Sorry, maybe he towed up to, yeah, I think it was that, 9,000, and he went back. So we did those very high flights to try to do that. We had this one that was not really high. But yeah, we are trying to do that. The other option, Troy, is to go really close to the ground, because then the atmosphere over the runway, then the atmosphere is probably calm there as well. But we're just not brave enough to dive Nixus at 140 knots close to the ground, and then, you know, slow down and land.
That's prudent.
Yeah, we're not taking that risk.
Well, I can say from experience that the level decel test is one of the most impressive things you'll do from a piloting perspective, because you get it ripping at 140 knots and then you level it off and it just goes and goes and goes and goes. I mean, I think we leveled off over Paso, over the airport, and I think we ended up finally turning around for another run, and we were out by Bonnell, which is 4+ miles away. So you got to have a lot of flat terrain away from the airport if you want to do that down low.
Yeah.
You typically do the opposite of that with aircraft. You do a level XL to get the drag polar. So that's really interesting to do it backwards.
Yeah, so the inspiration came from the level acceleration. But yeah, with the glider, there's no way to accelerate the glider. That's why we're doing this. I have a document here with the time that it took to do this. Well, I remember something like over 3 minutes to go from 140 knots to stall speed.
Yeah, that feels about right.
I have a quick question.
Go ahead, Will.
So in some of my reading about the way Akaflieg does their testing, I've read that they specifically do it with a comparison glider, because they're worried that things like high pressure or low pressure systems could have the atmosphere moving at, you know, very small but consistent rates and affect the data. Did you look into that at all?
Well, here in the US, we don't have a calibrated glider. So
that is an issue.
yeah, the DLR has that calibrated glider. Don't ask me how they calibrate a glider, because I'm pretty sure that's another PhD to do that. But the goal here is we don't have a calibrated glider, so how to do that? And I agree, the atmosphere has a huge impact on this. But when you're repeating the test multiple times with different times and you get the same result, I think that's good enough. You had something to say, Troy?
Yeah, I recall taking the courses at NTPS. We had temperature and pressure correction techniques, but you need to measure that stuff accurately while you're doing the test to make those corrections.
Yeah, but the beauty of this, I don't need any correction for temperature here. If I'm measuring, well, the only correction that I need for temperature is calculate true airspeed, which we do have good temperature sensors on the glider because the electronic variometer total energy works based on those. So we're using that one, but despite that, it's just measure specific energy and that's it. And the other thing is, you know, no matter how much times I measure this, what really matters is just go fly. And Sergio, the owner, was like, oh, we need to change this. I said, Sergio, first year of the glider and 5 national records, 2,400 kilometers. Why to measure this? It's just go fly. It's performing well. And a bad pilot decision will compensate for all this, or vice versa. A good pilot decision will make it better. There is a point that as an engineer, I want to measure this precisely because I know every time the glider is different and there's a lot of stuff. Okay, so because our time is probably over, there is a lot of more stuff that we did. I don't think it's worth to go into the details, but like 2 of them that are kind of interesting. One is this one. We actually did this before the summer, but here you can see on this left side, servos 1 to 6. And you can see there is a big portion of the flight that this servo just disappeared. It means the servo is off. And there is actually a portion here that there is no servo running. So all the fly-by-wire system is off. And then you can see on this bottom right chart is the angular rate to aileron input. And then you can see how you lose roll rate. So when no servo is running, it's just that very outboard aileron that's doing some mechanical actuation. And we get about 1/3 of the maximum roll rate of the glider, which gives us a lot of confidence. If the fly-by-wire fails completely, you can still fly that glider. Unfortunately, we did test that on a takeoff by accident. So we forgot to switch on the fly-by-wire, and the takeoff worked fairly well. Kind of lazy, the glider, Jim said, but it did work really well. That was, you know, those risks that normally we take and we shouldn't, but unfortunately it happened. The other one that's interesting is the power consumption. Here, this chart shows all the flights up to this day. Not really all the flights, I missed some of them, but I'm doing a battery data logger, and I log all that information so I can see what is my power consumption. And it's been very consistent, about 4 amp hour, which today gave us about 17 hours of flight with a 5% reserve, just pretty good. On this other chart, you see how current changed on the flight. And it's very interesting. The top one is a thermal flight. So you see a lot of current at low speed when you're rolling to thermal. And the bottom one is a wave flight. So you see a lot of current at high speeds now that you're flying straight, very little thermaling. But no matter if it's a thermal flight or as a wave flight, they kind of fall on this 4 amps per hour. And I think that's it. That's what I have to show you today. I hope to give you, for the Cal Poly students that are joining Akaflieg, a good taste of what we could do next summer.
Awesome. Well, thanks a bunch. If there's any other questions, go ahead and throw them out there. Okay, well, thanks a bunch for the presentation. And yeah, I hope everybody enjoyed it, and have a good evening.
See you guys.
Thanks, Will.
Thank you.
Thanks, Paulo.
Bye.
Thank you, Dr. Iscold.
Thank you.
Thank you.